Work yesterday. All we did was went over the administrative stuff with the syllabus um, and all the class procedures. And then we did that basic little presentation on a number and the structure of a number and how it interacts and our different forms of numbers. So I want to take a little time today to look at how does that really tie into the bigger picture. What the calculations you do all the time don't look like what we did yesterday. So the concept that ties this all together is another one of those basic concepts that's undervalued and misunderstood. And it's the concept of place value. Somebody with a lot of background noise, if you want to mute your mic for me if you're at home. Thanks.
Yeah,
So for
okay,
place value,
I gotta figure out how to do it.
if you move your mouse over the thing at the top of the screen, there should be a little thing that's a microphone. You just click on that, it'll mute your audio. Oops, I think you got your camera. There you go, you got the microphone too. Perfect, thank you. So for place value, again, I'm not going to insult you by going over this in a lot of detail, but if you start at the end of the number or where the decimal point is and we work our way backwards, here we have the ones and the tens and the hundreds place. And those are actually our only three place values. They repeat over and over again. Ones, tens, and hundreds. And ones, tens, and hundreds. And of course, this is our base group here. This is the thousands group. And then the millions group and the billions and trillions and on up the line. And when we name a place value, of course, we name its place value and its group. So this is just the tens place, this is the 10,000s and the 10 millions. And again, repeating. And like I said, I'm not going to insult you by going through pronouncing numbers or anything like that. But there are some reasons why these place values are important to us. One of them actually is in problems that look like this. Round 3,872 to the nearest 100. Now, some of us might be a little rusty on this, but we've all done it and we know how to do it. But let's look at what it really means. When it says round to the nearest 100, what it's really saying is assume that we have a number line that's only numbered in hundreds. So this might be 3,700, 3,800, 3,900, 4,000, and continuing in both directions. And it's saying if we take this number, 3,872, and put it on that number line, physically, which 100 is it closest to? Well, here it's closest to the 3,900. So it rounds to 3,900. Now, we don't want to have to draw out a number line every time we round numbers. That would be pretty tedious. So we've learned a shortcut. And the shortcut we learned is rounding to the nearest 100, you find the digit in the hundreds place. Here, that would be the 8. Well, that's telling us that we're between 3,800 and 3,900. To tell us which one we're closest to, we look at the next digit. If that next digit is a 1, 2, 3, or 4, well, then it's obviously closer to the smaller one. If it is a 6, 7, 8, or 9, it's closer to the larger one. Well, the big question always is, what if that next digit is a 5? Whereas here it was a 7, so it was closer to the larger number, the 3,900. But what if this was 3,852 instead of 72? Well, there's our hundreds digit, the 8. So again, we're between 3,800 and 3,900. That next digit is a 5, and 5 is right in the middle. However, it's not just a 5, it's a 52. It's slightly past the middle. It is closer to the larger number. We've always been taught when that next digit is a 5, we round up. If you asked your teacher why, they probably just told you that, well, it's a convention. We've accepted that that's what we're going to do. We just do it. There is a reason why. Most of the time, there's other stuff that comes after the 5 that truly does make us closer to the larger number. The only time it's really a factor is when there's nothing else after the 5. If we were rounding this to the nearest 100, well, the 5 is the next digit, nothing else after it. We really are exactly in the middle. Well, we still round those up anyway. That would still round to 3,900. In this class, that's the way we're always going to round. If that next digit's a 5, we round up. For those of you in automotive, you may run into in mechanical engineering and mechanical design, they worry about error buildups. So if you round all of those 5s up, you sometimes run into trouble where if you have several dimensions or several numbers that are used together, by the time you get to the end, you're way larger than you need to be. So they have some processes where sometimes you round up, sometimes you round down with that next digit's a 5. I'm not going to go over it in here just because I don't want to confuse you, but be aware that it is a process, and if you see it, they didn't make a mistake. They're just trying to avoid those error buildups and tolerance buildups. By the way, since we mentioned a number line, I'm going to bring this up. We've all seen problems like this where they ask you to fill in, less than, greater than, or equal to. Of course, here it would be greater than because the 8 is bigger than the 5. And what a lot of us were taught, trying to remember which of these is less than and which is greater than. But we were taught, the alligator eats the bigger number. So the jaw is open to the bigger number. Well, where that symbol really comes from is off that number line. We have the 5 and the 8 on the number line. What this is asking, what this is really saying is 8 is on this side of 5. That greater than symbol comes from the end of the number line, the larger end of the number line, and the less than symbol comes from the smaller end of the number line. Okay, so anyway, back to place values. So these place values define how we interact with our larger numbers, staying consistent with what we talked about yesterday with the count and the name. Let's look at something like 374. That's how we're used to seeing that written, but it's actually just an abbreviation. The full form of that number looks like this. 3 hundreds, 7 tens, 4 ones. And once it's in that form, we can see that each digit has a count and a name. This is not just a 7, it's 7 tens. And when it's in that form, when we go to do an operation with it, the process becomes more apparent. Let's say we're going to add that to 425. Well, let's write that out in its full form. That's 4 hundreds, 2 tens, 5 ones. And remember, yesterday we said that when we add or subtract, we can only combine things that have the same name. That means that this 7 tens can only be combined with these 2 tens. This is why when we were taught to add and subtract, we're taught you have to add up the columns. Ones with the ones, tens with the tens, hundreds with the hundreds. Because when we add or subtract, we can only combine things with the same name. Once they're lined up, we can go ahead and add. 300s and 400s make 700s. 7 tens and 2 tens make 9 tens. 4 ones and 5 ones make 9 ones, giving us 799. Now, if you were paying close attention there, you might have caught that I did something a little bit strange. I started on the left and I went to the right as I calculated. Most of the time, we start at the end of the number, the right end, and work our way backwards. We do that in case we have to do what? Carry, very good, yes. 480, let's do something like 486 plus 297. We start on the right side and work backwards in case we run into this. 6 plus 7 is 13. Well, we can't have two digits there, so we keep the 3 and we carry the 1. 1 and 8 is 9, plus 9 is 18. Again, we can't have two digits there, so we keep the 8 and carry the 1. 1 and 4 is 5, plus 2 is 7, giving us 783. Well, believe it or not, that process of carrying is actually a relatively new process. Now, in math, when we say relatively new, that just means in the last couple hundred years. But before carrying was a big thing, one of the ways you might have added could have looked like this. 4 plus 2 is 6. 8 plus 9 is 17. So 7, drop the 1. 6 plus 7 is 13. So 3, drop the 1. 6 and 1 is 7. 7 and 1 is 8. And the 3. We get the same answer. Now, this takes a little more space and maybe a little more time, but we get to the same result. I have a couple of points to make here. One is, what we've been taught here is just shortcuts. We've been taught to shorten it and make it smaller and fit in a smaller piece and fewer steps to make it quicker. But there are longer processes out there that really fit what we've been taught. The second point I want to make is we've always been told there's only one right way to do math. That's not really true. There's only one correct answer, but there are several different processes you can go through to get to that answer. If we had time, I could do 2 or 3 other ways of adding numbers that would give us the correct answer every time that looked very different. I'm not going to do it because I don't want to confuse you, but they're out there. So the point is, if you have a way of doing things that's different from what I show you, that does not mean you're wrong. If you're not sure if it works every time, let me know, and I'd be happy to look at what you do and let you know if it's something that works every time. The important thing is to find something that makes sense to you. Everybody's brain is hardwired to do math. People say, oh no, I can't do math. My brain doesn't work that way. Yes, it does. Everybody's brain is hardwired to do math. Math is a physical part of nature, so your brain can do it. It's just not everybody's brain is wired to do it the same way. So you have to find the way that your brain connects with math and figure out the processes that fit in with the way your brain works. So I'm not trying to force everybody to do things the same way. Now, the realist in me comes out at this point and says, you have the calculators, you're going to use them, and I'm not going to try to stop you. When you get to 3-digit numbers, most of you are going to use the calculator. So I hope that at the very least you look at a problem like this, and before you punch it in the calculator, you think, well, 486, that's close to 500. 297, that's close to 300. 5 and 3 makes 8. Hundreds and hundreds stays hundreds. We keep the same name. So I'm expecting an answer close to 800. So that when you punch this in the calculator, and the calculator comes up with 783, you know that that makes sense. Well, why do I bother to take that little bit of time to do that? Well, because it's very common for something like this to happen. 486 plus 297. Well, 343 doesn't make sense. What happened there? Well, you can see in the 486, the 8 didn't register when I pressed it. I either missed the key or didn't press it hard enough. It didn't come in. So if I'm expecting 800, I know that this is not right. There's no way that can be correct. The other thing that sometimes happens looks like this. 486 plus 297. Well, 5,000 does not seem correct either. When I punched it in, I accidentally hit an extra key when I was doing the 486. So having that idea before you punch it in the calculator helps to catch the worst of those mistakes. It won't catch all of them, but it's going to catch the worst of them. Otherwise, I've seen a number of people that have that happen. You miss key on the calculator. You take that number you get and you use it in your next calculation, and all the work you've done after that point is useless because you didn't catch that calculator mistake. Subtraction. We have said that subtraction follows the same rules as addition. So if I look at something like 784 minus 362, we can write these out in that full form. 700s and 8 tens, 4 ones. 300s, 6 tens, and 2 ones. And just like addition, we can only combine things that have the same name. I can only combine the tens with the tens, and the ones with the ones, and the hundreds with the hundreds. And once I have them lined up, I can go ahead and subtract. 700s minus 300s is 400s. 8 tens minus 6 tens is 2 tens. And 4 ones minus 2 ones is 2 ones, giving us 422. Once again, you may have caught that I did something strange. I went left to right. Typically, when we subtract, we go the other direction. 657 minus 298. We typically go right to left. We start at the end of the number and work backwards in case we have to do this. Well, 7 minus 8 can't be done. We have to borrow from the 5. This becomes a 4, and this is now a 17. 17 minus 8 is 9. 4 minus 9 can't be done, so we borrow from the 6. That's a 5, and this is now a 14. 14 minus 9 is 5, and 5 minus 2 is 3. Now, just like carrying, borrowing is a relatively new process. One of the ways that this might have been done before, or borrowing was the big thing, may have looked like this. 6 minus 2 is 4. 5 minus 9 can't be done, so we actually borrow from the 4 to make that a 3. This is a 15. 15 minus 9 is 6. 7 minus 8 can't be done, so we borrow from the 6 to make that a 5, and this is now a 17. 17 minus 8 is 9. You'll notice we get the same answer. Again, this may have taken a little more space and a little more time, but we get the same result. Again, my point is not to change how you do numbers, but to point out that there are different methods that are going to get us to the same results. Now, again, I realize the calculator exists. I'm not going to deny you from using it. 657, I'd hope at the very least you look at that and say that that's about 700. 298, that's about 300. 7 minus 3 is 4, and we keep the name of hundreds. I'm expecting an answer close to 400. So when the calculator spits out 359, we know that that's a reasonable answer. It's around 400. Now, I said that I'm not going to deny you the calculator, but I will mention this on our first quiz. There are 6 problems. You can use the calculator on them, but I also force you to show your work. So you do have to set them up at least like this and show your borrowing and stuff when you subtract. You can use the calculator to double check it. You can use the calculator to combine individual digits if you need to, but I do want to see you at least work them out long form to show the steps. Just this once, only on quiz 1. After that, I won't make you do that ever again. That quiz is coming up next Tuesday, by the way, just so you're aware. Anyway, let's talk about multiplication. We had mentioned yesterday multiplication and division. The big difference from addition and subtraction is when we multiply or divide, we do not need the same name because we're going to combine the names when we multiply and divide. So let's write this out in long form again. 32 times 21. Well, 32 is 3 tens, 2 ones. 21 is 2 tens, and 1 1. So because we don't need the same name, this 3 tens here not only can combine with the 2 tens, but it can also combine with the ones. In fact, every digit in one number can combine with every digit in the other number. And that's all long multiplication is an organized method of making sure that every digit in one number gets combined with every digit in the other number. The difference from one method to the next is where we start and how we organize it. Most of us were taught you start with the bottom number and the last digit. So we'll start with the 1, 1. And we combine that with the top number, starting with the last digit of the top number. So let's multiply 1, 1 times 2 ones. Well, combining counts, 1 times 2 is 2. Combining names, 1s times 1s is 1s. Then we move over to the next digit in the top number. 1, 1 times 3 tens. Well, 1 times 3 is 3. 1s times 10s is 10s. We've now combined with every digit in the top number, so we move over to the next digit in the bottom number. And we've been taught that when we do that, we either have to leave a space down here or put in a 0. The reason for that's going to be apparent here in the next step. So we take the 2 tens times the last digit in that top number times the 2 ones. Well, 2 times 2 is 4. But remember, we also have to combine the names. 10s times 1s is 10s. Putting in this 0 here is just making sure our place values stayed lined up. 2 tens times 3 tens, well, 2 times 3 is 6. Multiplying the names, 10s times 10s is hundreds. So you can see part of the organization was making sure that the place values stayed lined up throughout the process. Now we've got 2 1s plus 0 is just 2 1s. 3 tens and 4 tens is 7 tens. And 6 hundreds. And so that is 672. I won't show you alternative methods of multiplication because it does get a little confusing. But again, the only difference is where you start and how you organize it. It's still all methods of long multiplication are just making sure we combine every digit in one number with every digit in the other number. Again, I realize you're going to use the calculator, so I hope that you at least say that's about 30. This is about 20. Now, when we multiply, we combine counts. 3 times 2 is 6, but we also combine the names. 10s times 10s is hundreds. So I'm expecting an answer around 600. 672 is in that ballpark. Well, let's take a second to look at how we combined those counts. In addition, combining counts, I realize I haven't done division yet, but there's a reason we'll come back to it. In addition, combining counts really comes down to the number line. If I have 5 plus 3, it comes down to representing those numbers with vectors. 5 is represented as a vector or an arrow. That starts at 0, goes to 5. That's the representation of that count of 5 on the number line. 3, of course, then would start at 0, go to 3. The process of addition is taking those values, those vectors, and putting them together to make one long vector. So you can see when I put them together, it goes to 8. 5 plus 3 is 8. Well, we've all added 5 and 3, and we all know 5 plus 3 is 8. So we didn't really need the number line to do that. In math, addition is really, this process here of combining vectors with addition is really the only process of combining counts that exists. We'll come back to subtraction later on when we do negative numbers. But let's talk about multiplication. If you think back to first grade or so, when you first started multiplying, if you were asked to do 5 times 3, before you memorized that that was 15, the way we figured it out was this: 5 plus 5 plus 5. Repeated addition gave us that 15. If we're going to go back to the number line, what we were being asked to do there was take that vector for 5 and repeat it 3 times. So multiplication was just repeated addition, repeating that vector over and over. Well, we said that multiplication and division are the same operation, just one's forward and one's going in reverse. So if multiplication is repeated addition, division can be repeated subtraction. 24 divided by 8 means I start with 24 and I start subtracting 8. 24 minus 8 is 16. I subtract another 8, I'm at 8. I subtract another 8, I'm at 0. I subtracted 8 1, 2, 3 times. 24 divided by 8 equals 3 because I can subtract 8 from 24 3 times before I run out of value. However, that repeated subtraction only goes so far. If I have 72 divided by 3, I don't want to start subtracting 3 from 72. That's going to take a lot of time. But what we can do, rather than subtracting 3, is we can subtract bundles of 3. Well, how do I know how big of a bundle? Well, I use the place values of the number I'm dividing. The largest place value here in the number I'm dividing, in the 72, is the tens place. Let's use that place value. 10 times 3 is 30. I can subtract 30 from 72. In fact, I can subtract it twice. 30 times 2 is 60. I subtract 72 minus 60, I'm left with 12. Well, what does this 60 really represent? I subtracted a bundle of 3 2 times. Sorry, a bundle of 10 threes 2 times. So 10 times 2 is 20. That 60 represents 20 threes being subtracted, subtracting 3 20 times. Now, of course, my next place value is just the ones place. Don't really need to do this, but I'll do it out to be consistent. 1 times 3 is 3. And, of course, 3 times 4 is 12. So I subtract 12. 1, but 0. So I just subtracted it 4 more times. So 20 and 4 make 24. 72 divided by 3 is 24 because I can subtract 3 from 72 24 times. But as you can see, I didn't have to actually physically do it 24 times. I could subtract it in bundles of multiple threes rather than doing it individually. Now that may look like a strange thing that I just showed you, but that is actually our process of long division in a nutshell. All our process of long division is an organized way of making sure we can subtract that number over and over again. So if I take something like 7,854 and I divide by 21, I am not about to start subtracting 21 from 7,000. We don't have that kind of free time. But I can look at subtracting a bundle of 21s. So I look at my place value here. That's a 7. That's in the thousands place. So I do 1,000 times 21. That's 21,000. That's too big. I can't subtract it. So I go to the next place value. My hundreds place. 100 times 21 is 2,100. I can subtract that. In fact, I can do it more than once. 2,100 times 3 is 6,300. Got 4, 5, 5, and 1 left over as I subtract. But what I just did there was I had a bundle of 121s, and I did it 3 times. 100 times 3 is 300. That 6,300 represents subtracting 21 300 times. Well, next place value is the tens. 10 times 21 is 210. I can subtract that from what's left. In fact, I can subtract it, looks like 7 times. 210 times 7 is 1,470. That'll give me 4, borrow here, and 8, 84 left. Well, again, what I just subtracted there's a bundle of 10 of those 21s, and I did it 7 times. 10 times 7 is 70. This 1,470 represents subtracting 21 70 times. And finally, I'm down to the ones place. 1 times 21 is 21. I can take 4 of those. 4 times 21 is 84. Leaves me with nothing. So I just subtracted 21 4 more times. Technically, I could do 1 times 4 is 4. So this gives me 374. 7,854 divided by 21 is 374. Now you might be looking at that thinking, that looks absolutely nothing like what I was taught for long division. And it doesn't look anything like it, but it's actually exactly the same process. Let me show you. 7,854 divided by 21. What we were taught to do looked something like this. Look at the first digit. Does 21 go into 7? Well, no, 7's too small, so we leave it blank above the 7. That's exactly what we did over here. 1,000 times 21 was 21,000. That was too large, so we went to the next place value. So we move over to the 8. 21 goes into 78 3 times. 3 times 21 is 63. Again, notice that's exactly what we did over here. We just left off the zeros. We subtract there. We get 15. We bring down the next digit of a 5. 21 goes into 155 7 times. 7 times 21 is 147. Again, it's exactly what I did over here. I just left off the zeros. We subtract there. 8, and we bring down the 4. 21 goes in 84 4 times, and we're done. This is much shorter, much neater, takes a lot less space. But it's also a process you had to memorize. Over here, yeah, there's a little bit of a process, but it makes sense. We're trying to figure out how to subtract that 21. What we were shown here, this process that we were taught, is really this process with just all these steps eliminated and shortened so that we can do it quicker. To me, once you learn this over here, this makes way more sense to me. I'm not going to force you guys to learn it, but I'm one of those people that I like to understand what's the root cause, what's the base process going on here so I know why things are done the way they are. Now again, I'm still a realist. Long division, by the way, is the one operation I try not to have to do by hand if I can avoid it. So I realize you're probably looking at this and you're going to say, well, that's about 8,000. That's about 20. 8 divided by 2 is 4. Thousands divided by tens is hundreds. So I'm expecting to get an answer close to 400 so that when you punch it in the calculator and it comes up with that, you're okay with it. Okay, so for today, we're going to get our first homework assignment. Our homework assignment is out of the book. It's pages 8 through 10. It's labeled, I think it's labeled exercise 1-1 or something like that. But there are problems 1 through 69, the odd numbered problems. I am actually going to post in Blackboard here in a little bit the solutions for the odd problems. will be posted in Blackboard so that you can check your answers as you go. I don't have them up there yet, but I will have them up there soon. In the next hour, I'll have them posted up there for you. I do that for a couple of reasons. Like I said, I don't collect your homework, so I want you to be able to check it yourself so that you know you did it correctly. But also, I don't want you to do 10 or 12 problems and then realize you're doing it wrong, because now you've developed a bad habit that you have to break before you can learn how to do it right. I want you to check your answers as you go to make sure you're doing it right as you go so you're not developing any bad habits. Now, just like I said yesterday, I do not collect homework and grade it. It sounds like I'm encouraging you not to do your homework. That is not the case. It is very important to practice. The only way to learn math is a famous quote, and I can't remember who said it. The only way to learn math is to do math. And this was said in the contents of a learning forum where they were saying you can read about history and learn about history. You can read about science and learn about science. You cannot read about math and learn math. Math is the one topic you have to do to learn. But what I am saying is when you're doing these assignments, the first few problems might be pretty easy. And if you're looking at them, they are really easy. Please do feel free to skip ahead towards the end of each section and at least do some of the more difficult problems and the word problems, because those word problems are going to be very similar to what you're going to see on quizzes. It's easy to look at these and say, oh, that's easy, I know how to do it. But sometimes you attempt to do a problem and you realize you maybe forgot a little piece, or it's not as easy as you thought. So make sure you are at least doing some of the more difficult problems. To me, the purpose of homework is to learn. So as long as you are putting in the effort to do the assignment, you're going to get those points. Like I said, I'm not going to collect them. We'll have 8 minutes or so of homework time. So as long as you're here working on homework for that 8 minutes, you're going to get those points. Just make sure you're doing enough homework to be prepared for the quizzes that come up. So as long as you're not, struggling with the quizzes, I won't give you a hard time about homework. So with that, we do have 8 minutes left. I will give you the last 8 minutes here to do homework. I will end the recording for you, and I will stay on the network so that I can answer any questions for you if they come up. So go ahead and get started.